Hello and welcome to lecture 20 of the course Theory of Computation. In this lecture, we will see push-down automata. Right? In the previous lectures, we had seen context-free grammars and the languages resulting from context-free grammar, which is context-free languages. Right? So, in this lecture, we will see push-down automata. In fact, what we are going to see is actually non-deterministic push-down automata, right? So there is so just like we had deterministic finite automata and non-deterministic finite automata, we have deterministic push-down automata and non-deterministic push-down automata. But unlike regular finite automata, where in the case of finite automata, both deterministic and non-deterministic finite automata have the same power. So both recognize the class of languages which are regular languages, right? Over here, that is not the case. So this is different in terms of computation power from deterministic push-down automata. Okay. So non-deterministic push-down automata is different in terms of computation power, meaning there are languages that we can recognize by using non-deterministic push-down automata, but we cannot recognize using deterministic push-down automata. So the non-determinism really adds some value. In other words, in the case of finite automata, you could convert a non-deterministic finite automata to a deterministic finite automata. Here we cannot do that, right? So there are reasons. However, in this course, we are not going to see the deterministic push-down automata. So whenever I say push-down automata from now on, it is going to be the non-deterministic one, right? So we will not talk about deterministic push-down automata at all. Okay. But then just for the completeness, I would like you to know that there is something called deterministic push-down automata, and the deterministic push-down automata has a slightly different computational power, meaning there are languages that are recognized by non-deterministic push-down automata which are not recognized by deterministic push-down automata. So this is in terms of computation, this is very much like a NFA, which is non-deterministic finite automata. Right. So push-down automata are also abbreviated by PDA, push-down automata. Right. So PDAs are like NFAs, but there is an additional stack for computation. So the stack is like a data structure that we may have learnt in data structures. So it is basically it's an infinite, it's an ideal stack. So it has infinite depth, right? It's at unbounded depth. So basically we can there is no limit, it's not a limited memory, it is an unlimited memory, but there are restrictions on how we can access them. So in very simple terms, in the case of NFA, we had so if you look at the figure, like there is a tape, let's say it contains some input. So 0 1 0 1 1 1 0, right? So this is the input, right? This is the input, and we just read the input and then make transitions as per the rules, right? That's what we did in the case of NFA. In the case of DSFA as well, but in the case of NFA there are more flexibilities. In the case of push-down automata or PDAs, we have this additional stack at our disposal, right? So this is a stack, which means you could let's say you could push or pop things from it, right? So stack is like you can think of it as a stack of plates or stack of books or something. So you could keep adding things to the top of it, but with the restriction that you cannot remove things. You can remove the top book or the top plate. You cannot remove things from the bottom, right? If you try to remove things from like in a real life stack of books, then things get messy. But in the case of the data structure stack, you are not allowed to remove things from the bottom or the middle, right? Whatever is at the top you can remove, and then once you remove that, you will see the next item, the one below the top, which is a new top. Now you can remove that, and like that you can remove, right. So the stack also may have some symbols, let's say A, B, something, right. So now if you add, maybe just to give an illustration, if you add a C on top of the stack, right, if you add a C on top of the stack, maybe I'll use a different color to denote that. So the C will go and sit on top of this, right. And if you want to remove the elements of the stack, you cannot remove from anywhere, you will have to remove from the top, right. So this is the stack, and the key thing is that the stack is not a fixed memory, right. So in theory, there is no limit to how many items how many symbols you can push down the stack, right. So that is the stack, right. So it is going to be an NFA with the stack, right. So that's what I have written here. In addition to moving between the states, so an NFA moves between the states, and in the case of a push down automata, it can also do push and pop symbols to the stack or from the stack, right. And in the case of NFA, we just saw the next symbol and then made the transitions. In the case of stack, in the case of PDA, we may also look at the next symbol of the stack, right. So in the figure that is above, we say that the next symbol in the input is 0 and the top of the stack is C. So then we may say that now you push a new symbol into the stack, and then you make the transition Q1 to Q3 or something, right. So the transitions will depend on what you see at the stack as well as what you see at the input, right. It can depend on what you see in the stack, it need not depend also, right. So we could just make a transition based on the input, we could also make epsilon transitions, right. We could also make a transition just based on the stack, right. So any combination is possible. So that is what I have written the second line. The state control also moves based on the symbols seen from the stack, right. So I will just make the formal definition. The formal definition is that a push down automata, that is singular automaton, is a 6 tuple q sigma gamma, okay. So this is new, q sigma gamma delta q0 f. So where q sigma gamma and f are finite sets. So this is exactly the same as what we saw in the case of NFAs, right, non-deterministic finite automata, where you had q sigma delta q0 f, also in the case of DFAs, but we did not have a gamma, right. So what is gamma? Gamma is the alphabet for the stack. So this need not be the same as the input alphabet. You could use other symbols for the stack. You could use a disjoint set of symbols. If you need not use a disjoint set, you could use the same set of symbols, or like a superset or subset, or some combination is also okay, right. So where q is a set of states, sigma is the input alphabet, gamma is the stack alphabet. So all of these are finite sets, right. And Q0 is the start state, just like in DFAs or NFAs, and F is a subset of the set of states, which is the accepting state, right. So the main thing that is going to be different is the transition function, right. So in the case of NFA, the transition function was like this: delta q cross sigma, right, going to a set of states, right. So in NFA, so I will just make some space here. These are finite sets. So in NFA, we had this transition function, where depending on what state you are in and depending on what symbol you see as part of the input, and also epsilon transitions are allowed. That is why we had this, we have the subscript epsilon. we can go to some subset of states, right. So it could be like, so let us say the symbol A, you go to one state or maybe two state, maybe three state, all of this is possible. In the case of this is the case of NFA. In the case of PDA, the difference is this gamma here, gamma subscript epsilon, and also this gamma here. This is where it differs, meaning the PDA could read the symbol on the top of the stack, right. So which is the only symbol that it could access, right. It could read the symbol on the top of the stack, and then it could also write symbols on the top of the stack, or rather it could push symbols from the stack, and it could push symbols onto the stack. It can pop symbols from the stack also, right. So, and the transition rules can be based on what symbol it sees or what symbol it sees. So when it sees, it pops a symbol, and then there are some transition rules, and the transition rules may result in a symbol being pushed onto the stack also. So it is like an NFA, but in addition to all these states and the symbols that you read, there is a new dimension, which is that what you read from the stack. Again, we don't necessarily need to make reading from the stack at all transitions. We don't necessarily need to write into the stack at all transitions, but we can do both. We can do neither. We can do one. All four possibilities are there. We could just push without popping. We could just pop without pushing. We could both read and write, or push and pop. We could do neither. We could just completely ignore the stack for a transition and just based on the input symbol. Right. So since we have seen NFAs, maybe it's not that difficult to see. So let me formally define what constitutes acceptance of a string in the PDA, right. So we say that the PDA M, we say that the PDA M accepts the input W, right. If we can write W as like M symbols, W1, W2 up to Wm, okay. So M symbols, where, so I didn't use, so usually we use N for the length of W. So the reason we are using M here is that each Wi is in sigma subscript epsilon, meaning it could be empty string also, right. So like I could, for instance, I could write 1010, maybe I could write it as 10 empty string and 10 empty string, right. So because maybe I am using empty transitions in the middle, right. So this is also similar to what we had exactly the same thing in NFAs as well, and a sequence of states R0, R1 up to Rm, okay. This is also what we had in NFAs. The difference is this is the main difference. This is a new thing. This is where we we didn't have this in NFAs, different from NFAs, okay. So let's see what this means. So what is S0, S1, etc., and notice that these are part of gamma star, meaning these are strings that are formed using the stack alphabet, okay, which means actually it's like this. So suppose the stack contains suppose at some point the stack contains this string A, B, I don't know, C, A, okay. That's it, and that's the bottom, right. So now we will say at this stage the string corresponding to the stack is AB, CA, right. And in the next step I may push a string. So let's say I push A. So then the string in the stack becomes AA, BCA. I could pop something from the stack, right. So let's say I pop to the top A. So then the string in the stack becomes BCA, okay. So this is what I mean by string of the stack. right? And as usual, the rules for acceptance are similar to before. So we should start correctly, all the moves should be proper, and we should end at an accepting state, right? So this is the starting part, start correctly. So this means R0 is a starting state. So this is a start state, and this means stack is empty to begin with. We start with the start state, and then we say that the stack is empty. And the next rule says that all the transitions should be proper, right? Meaning at the ith move or at the I plus 1th move, right? So initially move 1 takes you from the 0th state, which is a start state, to the first state, right? So we want, so the state before, let's say the state before, let's say the state before the rule, the state before the ith step was Ri, okay. So this is what I mean by Ri, and okay, and the state before is Ri, and suppose T is the string of the stack, okay. So when I said that, what I mean is, so if you look at this figure that we have here, I called, if suppose this is what is there in the stack, so this is T, so in this figure T is sorry, I will just write it separately, T is AB, CA, right, because that is the string in the stack, right. Suppose T is what is already there, right. So and Ri is the state that we are in, and the next symbol that we are reading is Wi plus 1, right. So is Wi plus 1, right, and let's say the top part of the stack is A, which is actually the case here, right. So okay, maybe I should not have written T as this, I should have written T as one level lower, okay, everything but the top symbol. So T is, sorry for the confusion, T is BCA. So the top symbol is not part of T, okay. So this part, basically the top, it's only the top part that changes, okay. So when you at this point you are at state Ri, the next symbol of the input is Wi plus 1, and the top of the stack is A, right, the top of the stack is A. So that's how we have Ri, Wi plus 1 and A, and then there could be multiple rules corresponding to this. So notice that the rule is Q sigma gamma for a function of Q sigma gamma. So we have the state is Ri, which is in Q, sigma is Wi plus 1, which is the next symbol, the symbol in from the stack is A, right. Based on this, there are many possible things, for the next state and the next thing to be written into the stack. So suppose so what we want is, so if the sequence of states are to be valid, then we should have Ri plus 1 as a possible candidate here. So Ri plus 1 is the next state, right, and B should be, so suppose the symbol is B, right. So this is the symbol to be written into the stack, right, because if you remember in NFA there is nothing to be written because we only read the input, but here we have a stack onto which we can write things. So where suppose this is the stack, this is a rule. So now which means before the transition, the stack content was A followed by T, right, because we saw A, and the rest of the stack content we are calling it T, right, we are calling it T. and now A was read by this in this move, and we wrote B, right. So now what happens is this A was erased and we wrote B, right. So now A followed by T is now being changed to B followed by T, right. So now AT is replaced by BT. This is what I have written here. So before the ith transition, SI was AT. After the ith transition, the stack content is BT. So you are in state Ri and you read the next symbol Wi plus 1, you read the top of the stack A, and one of the rules is that now you move to Ri plus 1 and you replace the top of the stack with B, right. And therefore you get that earlier it was A followed by the string T in the stack, now it is B followed by T, right. So this has to be, so these has to be met every move. Basically every time if we have Ri Wi plus 1 A, which is the state, next symbol of the next symbol of the input and the top symbol of the stack, then the successor state Ri plus 1 and B should be such that it should be part of the transition rule. It should be a legal transition rule, such that the sequence of the stack contents are also preserved, are also maintained, right. So maybe when I say it like this, it seems a bit complex, but when we see an example, this will be clear. And like that, we make all these transitions. Finally, we reach let's say after you read the input, we reach the state Rm, right. Rm is the last state, and for the string to be accepted, this has to be a accepting state. So the only rule for accepting a string is that Rm is in accepting state. This is exactly what we had in NFA also, but in the case of PDA, push automata, we also have a stack. So one may wonder whether do we want something with respect to the stack, right. So one may think that if you have a lot of content in the stack, but at the end the stack is not emptied, do we still accept the string? So the answer is, when we accept the string, the stack need not be emptied. It is completely fine. The only thing is that once you read the input string, we should be at an accepting state. The stack need not be empty. Okay. In other words, in the sequence of stack, the strings that are in the stack, this SM, this need not be an empty string for it to be accepted, right. So these are the rules for accepting a certain string in the stack. It should be decomposed in such a way that it starts correctly, starting at the starting state, stack with empty, and each rule should be valid, right. Each transition should be valid. Ri plus 1 should be a valid successor of Ri, such that the Si plus 1, the next stack configuration, is a valid successor of the current stack configuration, and so A and B should be such that, and we read the correct input string. And finally, the last state should be an accepting state, right. So now let's just see couple of examples, right. So let's see this example and let's see what this PDA does, right. So there are 4 states. So interestingly, the first state itself is an accepting state, right, and I have to explain this notation. So what this means, let's take this notation, epsilon arrow $. This means that the one before the comma epsilon, this means that maybe I will do one thing. Maybe I'll explain the this one, because here there are 3 different symbols, right. So this means that, or maybe I'll just write here A, B goes to C. This means that read A from the input, So when I say input, it's the actual input, not the stack. And read B from stack and write C into stack. So any of them could be empty, right? Which means you could read nothing. You may read nothing from the input, you may read nothing from the stack, you may write nothing into the stack. So all three also can be empty, in which case it's just an epsilon transition. So one more point here, even over here, right? Even over here, the way I defined the transition, even over here, B could be empty. We may not write anything into the stack. A could be empty. We may not read anything into the stack. Wi plus 1, which is the next symbol in the input, that also could be empty. Maybe all three can be empty, right? Which means without reading or writing anything from the stack or into the stack, or even not reading the input, you may make the transition, right? If both A and B are in empty strings, that would mean that both Si and Si plus 1 are the same. So you are not reading anything from the stack, you are not putting anything into the stack, so the stack remains intact, right? Anyway, so A comma B arrow C means you read A from the input, you read B from the stack. When you read something from the stack, you are popping it, okay, and then you write C into the stack, which means you are pushing it. So what are we doing here? So first, this means the first transition here, it is basically dollar is inserted. Nothing is read from the input nor the stack. So you first insert dollar into the stack. Maybe I'll just use the word pushed instead of inserted. So if you are not familiar, usually we use the words push for inserting something to the stack and pop for removing something from the stack. So initially dollar is pushed into the stack, okay. So dollar is a special symbol that is in the stack alphabet, and then let us see what this loop does. So this means you are reading 0 from the input, right, and you are not writing anything. So you are not writing anything into the stack. Sorry, you are not reading anything from the stack, right. So this is epsilon, but you are writing a 0 into the stack. So you can go through these loops as long as you keep seeing 0 in the input, and whenever you see a 0, you don't read anything from the stack, but you write a 0 into the stack, okay. So it's like this. Let's say the string is 0 0, or let's say it starts with 0 0 0, right. So initially, without reading anything, you put a dollar into the stack. So maybe I'll just put it like this. You put a dollar into the stack, right, and then you read a 0 and you put a 0 into the stack. Then you read the second 0 and you put a 0 into the stack. Then you put a third 0 and you put a 0 into the stack, right. Suppose that is it. Now the next symbol is 1, let's say, okay. So now you cannot remain in this loop, and the next transition to the next state is by reading a 1 from the input. So you are reading a 1 from the input, which is what we have, and you are reading a 0 from the stack, okay. You are reading a 0 from the stack, this, but you are not writing anything into the stack, which means we are going to erase the stop 0, right. And now you come to the third state. I mean, let's say maybe I'll just call it Q1, Q2, Q1, Q2, Q3 and Q4. You come to the third state, let's say Q3. Now you cannot move to Q4 because you cannot immediately move to Q4 because Q4 requires you to pop a dollar from the stack. So you are reading a dollar from the stack, but right now you cannot read the dollar. The dollar is below the zeros. So if you want to pop the dollar, you should first pop the zeros. The only way to pop the zeros is by using this loop on the Q3, this particular loop, right. So if you want to pop a 0, you should read a 1. So now if you want to accept, you should read once, but right now we read 0 0 0 1 and we should have more ones. So if you have one more 1, you can pop it. You can pop one more 0. If you have another one more, then you can pop both the zeros, right. So at this point this is popped and this is also popped, and now you can pop the dollar. So now if you see, if the string was 000111, you would have popped the dollar and gone to Q4, which is an accepting state. But suppose you had 000111 and yet another 1. So in which case, after reading, let's say if you go to Q4 by popping the dollar, then there is still string left and there is no more moves left. Or if you were at Q3, you had popped the 2 zeros, right? You had popped the 2 zeros. You are at Q3, right? But there is one more 1. But you cannot even remain at Q3 now, because from Q3 there are only two options. One is remain at Q3 or go to Q4. If you go to Q4, it's fine, you can go, but there is one more bit in the string left. If you try to read the 1 at Q3 itself, that's also not possible, because reading the 1 requires you to pop a 0, and there is no 0 in the stack. So which means 0001111 is not going to be accepted. And similarly 0001 is also not going to be accepted, because if you read this, you will have a dollar and then 0 and then 0 like this, and you cannot move to Q4. So in order to get to an acceptance, you need to move to Q4. So if you're observing what is happening, so you initially push a dollar. For every 0 red you push a 0. For every 1 red you pop a 0. And then finally you need to remove the dollar as well. So the only way to get to remove the initial dollar that you pushed is whatever 0 you read, same number of 1s also should be read. So the string should be of the form. So the string, if this PDA has to accept, the string should be of the form 0 power n, 1 power n, the same number of zeros and ones. Only then, so whenever a 0 is read, you push a 0, and then whenever you read a 1, you pop that 0. So you also notice the significance of this dollar that is pushed and popped, because if there is no dollar that is pushed at the beginning, there is no way to tell the stack has ended, or no way to tell that you cannot read anymore. So this dollar is a special symbol that we are only pushing it once. That tells you that so you have read all the you have pushed some zeros, you have popped all the zeros. Now we are at the end. Whatever we have pushed, we have popped. This we need to know. Or let's say we have pushed all the zeros. We have not popped all the zeros. The next symbol is still 0, which means the dollar is buried under many other zeros. So this dollar is an indicator that we have reached the bottom of the stack. That is the significance of the symbol dollar, and that's what I have written here. This dollar is used to check if the stack is actually empty, because in the definition of the PDA itself, we said that upon acceptance the stack need not be empty, right? So that was not an essential thing. So this dollar is an artificial, it's kind of a workaround to ensure that the stack gets emptied. Okay, so this is a PDA for all the strings 0 power and 1 power n. So now already you see that this PDA is accepting a language which is not a regular language. In fact, it's a context free language. I think I mentioned this before. We will, after one or two lectures, we will see that PDAs, the class of languages that PDAs recognizes, is the same as context free languages. So we already know that 0 power and 1 power n is a context free language. So now we are seeing a PDA for it. So one exercise is to construct a PDA for all the strings that constitute properly nested parentheses. right? So things like this. Right, all these strings are properly nested and matching parentheses. So try to construct a PDA for this. I think we have seen a context free grammar, but try to come up with a PDA as well. Sorry. So now we will see one more PDA, which is for the language a power I, b power j, c power k, where either I is equal to j or I equal to k. Okay, so either the number of a's is equal to number of b's, or the number of a's is equal to the number of c's. So it is something similar to what we did here, where here we just had to check whether the number of zeros is equal to the ones, but here there is a choice to be made. So we use similar technique. We use the stack to check that number of a's is equal to b's, etc. But we do some we have to use one more trick, right? Before that, I just want to mention, so we are really using the fact that the stack can be potentially unbounded, right? Because 0 power n, 1 power n, how much ever big the n is, we can push that many zeros into the stack, because the stack does not have a bound. So that is why the stack has to be really unbounded. So that is where we are using that. So if we don't have an unbounded stack, then we cannot accept this language. So suppose the stack is limited to size 100. In that case, we can only accept 0 power 99 and 1 power 99, right? Because we have to push the dollar and then 99 zeros, and then we are stuck. In which case it's a finite language, in which case it's not a context free language. It's just it is a context free language, but it's a regular language also. It's a kind of trivial thing. So coming back, a power I, b power j, c power k, where the number of a's equal to b's or the number of a's equal to c's, right? So we do the same thing here. We push a dollar at the beginning, and we loop over here. We add an a into the stack for each symbol a that is read, and then we make this fork. There are two possibilities. So in the left side, we check for, in the left side we are checking for I equal to j, this side, and this side it is I equal to k. So in the left side it is, we are seeing whether the number of a's is equal to the number of b's, and the right side we are checking whether the number of a's is equal to the number of c's. And what is happening here? This is both epsilon transitions, right? So this is an epsilon transition, this is epsilon, meaning you read nothing from the input, you read nothing from the stack, you write nothing into the stack. So basically there are two, it's just like two, you basically take one of these two paths. In case of the left path, you see that for each b read, right, you are popping out an a. So the only way that we will be able to see the dollar next, right? So we will get to this, the last state, the accepting state in the left side, only if you are able to pop the dollar, and that will happen only when the number of b's read is equal to the number of a's. And once you are able to pop the dollar, you come to the accepting state, and then you can accept. So you will also accept, let's say, a power n, b power n, right? Even if there are no c's, that's okay. But then once, if the number of b's and a's are equal, now you can accept any number of c's as long as we only see c's. If we see a b here, we will not accept, because there is no transition available for a b. But c's, there are no limit, right? So you can keep seeing c's and you will still be in the same state. So, all the strings of the form a power n, b power n, c power m, or yeah, maybe I will say a power I, b power j, c power k, where I equal to j will be accepted in this state. The right side, it's similar. Basically, now we have already read some number of A's and we have pushed that many same number of A's into the stack. Then we are going to see these B's, and this there is nothing. We are seeing B's, but we are not doing anything to the stack. We are just remaining in the same state, right? We cannot read A's now once we move to this place. We cannot read C's also. And at some point we move to the next state, and then we are reading C's, and whenever we read one symbol C, we pop out an A, right? So that's what is happening here. Whenever we read a C, we pop out an A, and the only way we will move to the accepting state is if the number of C's is equal to the number of A's. And the way in which these are ordered, it ensures that the string has to be of the form A star, B star, C star. So the only strings that reach the last state here, the accepting state in the right side, is of the form a power I, b power j, c power k, where I equal to k. So the number of B's doesn't really matter because it doesn't touch the stack, right? That's what we saw here. So basically, it's exactly the same thing that we did here. But here we are matching. First thing is that we have a fork where we decide to check whether A is equal to B or A is equal to C. And the second thing is that when we are checking A equal to B, we have to kind of add the self loop for C where it does not touch the stack. And when we are checking whether A is equal to C in the right side, we have to make the self loop for B where B doesn't disturb the stack. So that's this for this language, a power I, b power j, c power k, I equal to j or I equal to k, we are able to construct a PDA. I think we are already kind of this lecture has gone slightly over time, so I think I will wind up with this part. So we saw what are push down automata, which is actually non-deterministic push down automata, although we will not be repeating that anymore. It is like an NFA with a stack, and the transition rules can be influenced by what is the stack content, right? And we explained when it accepts. So basically it has to make valid moves, and at the end it has to be an accepting state after having completely read the input, right? So then we saw some example. One was 0 power n, 1 power n, and this 2 was a power I, b power j, c power k, where I equal to j or I equal to k. We also had this exercise for properly nested parentheses that you can work out, and there are some other properties that we will see in the next lecture, but for now I just I'll stop now.